All right, part two, it's a separate set of notes. Today, we're going to be talking about the converse of the Pythagorean theorem. And so the converse of a statement switches the hypothesis and the conclusion of that statement around. So if statement number one is if P, then Q, then statement number two, the converse would say if Q, then P. And so if the Pythagorean theorem states that the Pythagorean theorem states that if a triangle is a right triangle, then a squared plus b squared equals c squared. The converse of Pythagorean theorem is going to state that if a squared plus b squared equals c squared, then that triangle is a right triangle. Switching the hypothesis and conclusion around. So switching around these two important things, right triangle, a squared plus b squared equals c squared. And now we're going to say today that if a squared plus b squared equals c squared, then you have a right triangle. The Pythagorean theorem is a theorem in which the converse of the theorem is also true. That's not true for every mathematical statement, though. For example, if you square a negative, your answer is positive. Is that true? If you square a negative, your answer is positive. Okay. So let me do the converse of that statement. If you square root a negative, your answer is positive. Can you square root a negative? Can't. All right, so this isn't something that happens for every theorem or even every mathematical statement, but it is true for the Pythagorean theorem. The converse of the Pythagorean theorem states that if you do your two legs, I know you don't know it's a right triangle yet, but if you do the two shorter sides, square them, and it equals the square on the longest side, and that's true, that means you have a right triangle. So let's look at the example A. It looks like a right triangle. Let's see if it is. If it were a right triangle, then 9 squared plus 40 squared would equal 41 squared. Chloe, what's 40 squared? Okay. Oliver, what's 41 squared? So if I add 81 and 1600, I get 1,681 equals 1,681. Is this a right triangle? It absolutely is. What about example B? Doesn't look like a right triangle. Doesn't look like it's a right triangle. Let's find out for sure. If it were a right triangle, 12 squared plus 18 squared would have to equal 24 squared. Because 24 is our longest side. We know the hypotenuse would have to be the longest side here. So someone who's already done their perfect squares. Lizzie, 12 squared. 18 squared. Emerson, 18 squared. 24 squared, Sky. So you know 576. Okay.
Yeah, I know everything after 22.
Next time I'll let you. You could have skipped over and kept going and come back to it. Like passing in a game show, like pass. You can come back to it if you wanted to. Okay. So can someone tell me what 144 plus 324 is, Owen? 468. So not 576. So this is not a right triangle. I guess the picture kind of gave it away, didn't it? Okay, no more pictures. 28, 21, and 20. Maddox, what would I try to do here if I'm trying to figure out if it's a right triangle? What would I plug in and to which spot into the Pythagorean theorem?
28 would go into C squared, which is the longest one, and then 21 and 20.
Okay, so basically it's saying, make sure the two shorter sides are being added together, the squares of the two shorter sides, because they're the two legs. If this is a right triangle, they are the legs, whereas the long side would be the hypotenuse. So 20 squared, 400, 21 squared, 441. We should know those. 28 squared, not in our list of 25 perfect squares though. Carter, what do you have?
784.
784. So add 400 and 441 together to get 841.
No.
Doesn't equal 784. I guess you could put like a does not equal sign between those two, like I should have done that last time. It does not equal. So this is also not a right triangle. All right, next. Pythagorean triples. You heard me mention those yesterday. A Pythagorean triple is a set of three natural numbers. Ooh, what's natural number mean, Owen? Starting at 1. Yeah, you're counting numbers starting at 1. They're all positive counting numbers. No decimals, no fractions, no zero, no negatives. So, and we said yesterday, even though some like negative numbers could satisfy the Pythagorean theorem, there is no triangle that has negative side lengths, so that's not going to work. So natural numbers. So three natural numbers in which a squared plus b squared would equal c squared. Here are some common Pythagorean triples, although this list does go on a long ways. The very first Pythagorean triple is the 3, 4, 5 Pythagorean triple. That's the most common one. We also saw yesterday the 5, 12, 13 show up, and we saw the 8, 15, 17 show up, and we saw this one. I remember specifically this one showed up. Was it the capture the flag problem that we did with your base and their base? I can't remember where it was, but there was a multiple of one of those that showed up. And so if you look at each list, this is just the 3, 4, 5 Pythagorean triple times 2. And this is the 3, 4, 5 times 3. And so when it says 3x, 4x, and 5x, they're saying as long as if you're taking one of those times 3, 1 times 4, 1 times 5, whatever that ratio, as long as that ratio is consistent, you're going to have a right triangle. As long as this ratio is consistent, you're going to have a right triangle, so on and so forth. Okay, so those are some Pythagorean triples. So the key idea from today is that if a squared plus b squared equals c squared, you have a right triangle. The question is, what happens if it doesn't equal c squared? Well, the easy answer is not a right triangle, but it could still be a triangle, right? Okay, so we're going to talk about two other types of triangles. We're going to talk about if it's not a right triangle, they have to be either an acute triangle or obtuse triangle. So if c squared equals a squared plus b squared, that is a right triangle. That's just the Pythagorean theorem on different sides of the equal sign. I'll show you in a minute why I did that. If c squared is less than a squared plus b squared, then you have an acute triangle. And if c squared is greater than a squared plus b squared, you have an obtuse triangle. This is where we're getting into the geometry part. What we just did was the 8th grade part of the lesson. Now I'm doing the geometry part, taking the Pythagorean theorem to the next level. If you can use the converse of the Pythagorean theorem to determine not just if it's a right triangle or not, but literally if it's an acute triangle or obtuse triangle as well. Now, if you're asking, why did I flip it around? Why does it say c squared equals instead of a squared plus b squared equals c squared? That's because I think in my mind, it makes more sense if I write it this way, because this is a less than symbol. And if c squared, if your hypotenuse squared is smaller than your a squared plus b squared, then you have a smaller triangle, you have an acute triangle. And if c squared is greater than a squared plus b squared, you have an obtuse triangle. Okay, so if your c is too long, I say too long, if it's longer than it, then what happens to the angle across from it? It widens out, obtuse triangle. Whereas if c squared is little in comparison to the other two sides, then you have an acute triangle. Okay, if angle opposite from it is going to be small. Okay, now there's a caveat to this. Remember a couple chapters ago, we talked about the triangle inequality theorem. It is possible that I could give you 3 side lengths that don't make a triangle. So the Pythagorean theorem or the converse of the Pythagorean theorem only works if you have a triangle, if the 2 shorter sides don't add, not the squares, If the two shorter sides themselves don't add up to be larger than the third longest side, remember, you don't have a triangle at all. Right? Remember our string? Our string, we tried to make a triangle, and there was one of the groups that couldn't make a triangle at all because I gave them a really long piece of string and two short edges, and it just couldn't happen. Right? It's possible that you can't make a triangle at all. So here, there's four options: right triangle, acute triangle, obtuse triangle, or no triangle. Now, here's the thing, though. You're going to have to test at the beginning whether or not it could even make a triangle. Because otherwise, you're just going to say it's obtuse. You're going to say, yeah, you have a long C side. Well, if it's too long, you don't have a triangle. So just because it satisfies this doesn't mean you have a triangle at all. We got to make sure that it is an obtuse triangle and not just no triangle at all. Now, with these triangles here that you're going to see, if I have a picture of it, then it's a triangle, right? We can assume that. But when I give you just the side lengths, we're going to have to check that. So this is what it looks like if you have a right triangle, obviously. This is what it would look like if you have an acute triangle, where the longest side is the square of that side is actually smaller than the squares of the two legs. Which, by the way, I say legs and hypotenuse. Those are only terms you can use in a right triangle. So, but I think you understand when I say legs, I'm talking about the two shorter sides. So I'm not accurate when I say legs and hypotenuse of an obtuse triangle, but you kind of get the idea. And that's what an obtuse triangle would look like, is if c squared is much bigger, or even a little bit bigger than a squared plus b squared. All right, so let's try that on this first example. Because of the way that it's worded, I'm going to start with my long side first, which is the 42 squared. And I'm going to see, is that equal? Question mark. Is that equal? Is it greater than, is it less than? I guess we'll find out. The 24 squared plus the 36 squared. Now we should know 24 squared. What's 24 squared? We should have that memorized. Owen? 576. Can someone tell me what 36 squared is? Lizzie? 600 and, oh, 1,296. Okay. And what about 42 squared, Christian? Okay. Now I add my 576 with my 1,296. Who's got that? Looking around for someone else to do it, are we? Lucy? 1,872. So if we were in our 8th grade textbook right now, we'd say, this is not a right triangle, and we'd close the book and walk away. But I want to know, what kind of triangle is it? Is c squared, so we know it's not equal. Is c squared less than a squared plus b squared, or greater than a squared plus b squared? Sky? It's less than, which means this is an acute triangle. If c squared is less than a squared plus b squared, then you have an acute triangle. So I like this because right and not right, that's lame. How about right versus acute versus obtuse? I like that better. What do you think about B? Would it be a safe bet to say obtuse for this triangle? Let's prove it mathematically. We know 24 squared is 576. We know that 18 squared is what? Come on, those of you that have done it, shout it out. 324. What about 12 squared? Okay. 324 plus 144 is 468. Is that right? Oops, I keep putting equals because I'm like used to doing that. Not actually equal at all. Is c squared greater than or less than a squared plus b squared? Jimmy? It's greater than. Yeah, so this is going to be obtuse. In fact, I think it's the same triangle we did up here. Is it the same one? Yeah, the 576 and the 6. Yeah, so instead of just saying not right, I prefer saying obtuse. Now, with this, You know what? Do these next two on your own. I'll pause the video. This time I'll try to actually pause it. Oh, I not did it again. Pause. All right, Shane, walk me through example C. Okay, does it matter what order I put the 20 squared and 15 squared? Okay, yeah, we talked about that yesterday. Now, these are all in your list of perfect squares you should know, right? So what did you have for 25 squared? 20 squared? 15 squared. Huh? Then what did you do? Oh, I forgot to put a question mark. That's not a big deal. I'm not gonna like super stickler if you don't put a question mark, because just know that I don't know if it's equal, right? Like I don't know if there's a what other symbol to put right there. I'm sorry, what did you say? Then what did you get for 400 plus 225? Oh, okay. So what kind of triangle did you say it was? A right triangle. Nice job. Yeah, excellent. Deegan, walk me through example D. Whoa, it's not a triangle. Why not? So if it were going to be a triangle, the two small sides have to add up to be greater than the longest side, not the squares, but the actual side lengths themselves, right? What is 7 plus 19? Yeah. So you have 26 is greater than 29, and that's not true. So this is not, you wouldn't say not right. You wouldn't say not acute. You wouldn't say not obtuse. You'd say not a triangle. It's just three lines, like flippers that never meet, right? They will never touch, unfortunately. They'll never touch. Okay, that's not a triangle. Now, this is the mistake that somebody's going to make on their quiz for next week. Someone's not going to be paying attention. Who's it going to be?
Me, because I just did that.
So you did the 7 squared. I'm sorry, we'll start with C squared. You did the 29 squared. And then you did the 7 squared and the 19 squared. And I know 7 squared is 49. I know 19 squared is 361. What's 29 squared, Carson?
I actually had it.
29 squared. 841. And then you added 49 and 61 to get 510. 510. And you said 841 is greater than 510. And since C squared is greater than A squared plus B squared, we have an obtuse triangle. So you put obtuse, didn't you? Anyone else do the same thing? A couple of you guys? Yep. It would be an obtuse triangle if I could get the segments to even touch, right? But they can't even touch because it's not a triangle. So please check, especially if you don't have a picture of your triangle. If I just give you 3 side lengths, check to see if it's a triangle at all before you check and do all that Pythagorean theorem work. Okay. All right, so this is all garbage work because we don't even have a triangle at all. Okay. So that was the geometry part of the homework. Let's get into the algebra 1 part of the homework. Simplifying square roots. The square root of a product equals the product of the square roots of the factors. Meaning, if I had the square root of 45, I could say that's the same as the square root of 9 times the square root of 5. Whatever's under the square root symbol, you're allowed to multiply those things together. Okay. How is that important? Well, in algebra, we like everything to be as simplified as possible, not just fractions, but also square roots. Yes, Guy? Yes, if that box is empty, there's more on the bottom shelf there. So when you're simplifying a square root, you're trying to pull an integer out of it. Well, sorry, a natural number out of it. The only way you're going to pull a natural number out of a square root is if there's a perfect square that goes into that square root. Yet another reason to know your perfect squares. So do you guys remember doing factor trees with prime factorizations? Okay, similar but different. We're still going to do a tree, but it's going to be a perfect square tree. What perfect square goes into 24? Owen? 8's not a perfect square. Your perfect squares are 1, 4, 9, 16, 25. Yes, 4 goes in, right? Okay. Now, 1 is always going to go in. Is 1 going to change? Or no, it's not. So please don't use 1. So the square root of 4 goes in square root 6 times. Like a factor tree, right? Except it's a square, it's a perfect square root tree. Now, the reason I asked if there's a perfect square that goes in is because what is the square root of 4? 2. So this is now 2. Or I guess, hold on. That's if you're, don't write what I wrote. Just put equals 2 and circle. I don't want to make it look like my tree's growing. It's not growing. Actually, that branch is now dead. Alive. It's alive. It's an integer. It's a natural number. Is there a perfect square that goes into the square root of 6? No. So then I leave it at square root of 6. So square root 24 can be rewritten as 2 times square root 6, and you just take those numbers and squeeze them together, just as if it was like 2x. You write 2 square root 6. That's how you simplify a square root. Now, instead of having a 24 under the square root symbol, we only have a 6 under the square root symbol. This is really useful when you get into algebra and geometry. You start adding the 2's and start doing other things with those 2's. Right now, we're just going to take that 2 and set it aside and say, okay, I could use you, and the square root 6 is all I have left. It's like making change. It's like saying, you know what I should do? Instead of having $1.57, maybe I should cash out and to get a dollar bill, 2 quarters and 7 pennies, or one nickel and 7 pennies. 2 pennies. I have no idea what I just said 7 pennies for. Okay, either way, so it's like I've got the same value, but I've got it, and I can use that dollar bill in the quarters more than I can use the nickels and the pennies. All right, example B. Is there a perfect square that goes into 80? Jimmy, what is it? Yes, 16 is a perfect square that goes into 80. Jimmy, how many times does it go into 80? That's right. Jimmy, you said 16 goes in. What is the square root of 16? 4. So this is going to be 4 times square root 5. That's what you would simplify to. What about 1600? Doesn't that 16 go in there too? Right? Okay. How many times does square root 16 go into square root 1600? Okay. And the square root of 16 is 4. Can square root of 100 be broken down? What perfect square goes into 100? Carson? 10 is not a perfect square. Are you saying, well, hold on. Okay. What are you saying? You're saying we could just say it's 10. Ah, so then we would just say 4 times 10. What's 4 times 10? Ah, okay. So square root of 1600 is just 40. In fact, if you type it into your calculator, just 40. Could I have broken square root of 100 down? I could have broken square root of 100 down into square root 4 and square root 25, both of which are both perfect squares, and then I'm going to get the same answer. Yeah, so this even works when the number you're breaking down is itself a perfect square. So it just goes to show that a perfect square times a perfect square is another perfect square. Okay. All right. How are these problems any different from the ones you had yesterday? They're not, except the way that you write your answer. Instead of rounding to the nearest tenth, like you did on the worksheet yesterday, and like we did in the notes, I want you to write your answer as a simplified square root or what is also referred to as radical form, reduced radical form. Simplified square root, reduced radical. I like the alliteration. So if I was doing this problem yesterday, I'd say that 6 squared plus 4 squared equals x squared. I would have called it c. They're calling it x. No big deal. What is 6 squared? Shout it out. 4 squared. Huh? 36 plus 16? 52. And so then you'd square root both sides, right? Okay. This is where our paths diverge. This is what, instead of, getting, what is that? 7.2 or something? Ha, 7.2. Look at that. You know how I knew that? What's the square root of 49? This is just a little bit bigger, right? So it's just an estimate. Anyways, instead of writing 7.2 as our answer, we're going to leave it in reduced radical form or simplified square root. We are going to just say, well, if x squared is 52, then x is square root 52. Just square root both sides, right? Is there a perfect square that goes into 52? Xander.
4.
Okay. How many times does 4 go into 52?
13.
Okay, so I know square root of 4 is 2. Is there a perfect square that goes into 13? No. Okay, so then my answer is x equals 2 square root 13. So all the work that's in red is what we would have done yesterday. Now we're adding the work that I did in blue, which is simplifying that square root down to 2 square root 13 instead of leaving it as 7.1 or 7.2. This is the most accurate answer I can give because I haven't approximated anything yet. Is it the most useful answer? Depends on what you're doing. If you're wanting to know how long that triangle is so you can buy enough mulch to mulch in your garden that length, then you're probably going to want the 7.2 feet or whatever yards, no labels. So whatever it is. But there are instances where that number is way more useful. Let's do the next one. Connor, am I missing a leg or a hypotenuse? Are you sure? Yeah, I was gonna say the hypotenuse is always across from the right angle. So I'm gonna do 7 squared plus x squared equals 14 squared. Connor, do you know what 14 squared is? That's right. Okay, one of them that we should know. We subtract 49 from both sides. Emerson, what's 196 minus 49? $147. Okay, all of that, same as yesterday, except now, instead of square rooting both sides and getting a number rounded as nearest 10th, we're just going to write x is equal to the square root of 147 and see if we can simplify it. Is there a perfect square that goes into 147? So, by the way, it is possible that a square root doesn't simplify. Fractions don't all simplify, right? Sometimes they already are reduced, but this one does. Xander, what's a perfect square that goes into 147?
49.
Ah. And how many times does 49 go into 147?
3.
All right. So we get our final answer of, and again, I don't really care how you show your work as long as you're showing it. X equals 7 square root 3. What do you think about this simplifying square root stuff? You don't like it?
Don't like it, but it's easy.
It adds extra work to it, doesn't it?
Yeah.
It's more accurate. Your answers on tonight's homework are going to require you to do it. Now, that being said, though, is that it? Huh, okay, cool. That being said, it is possible that if I gave you, like, for example, the square root of 10, and I said, all right, break that down. It doesn't break down. You could say square root 2, square root 5, but is 2 a perfect square? Is 5 a perfect square? So I'm back to this. nothing happened. Right? It only breaks down if a perfect square will go into it, so that when I square root that perfect square, I get a natural number, and then I can actually pull that out onto the outside of the square symbol. Okay, otherwise I'm going to be doing this until the end of time, right? So it's possible that it won't break down, just like it's possible for a fraction not to reduce, but some of them will. And so knowing your perfect squares is definitely an advantage for breaking down square roots. That's it. That's tonight's homework, and it's posted on Big Ideas.